All right, so let's get started on Chapter 3 material. Oh, and make sure you give me your test before you leave.
And our homework, right?
And your Chapter 2 homework, yes. You don't have to worry about that right now. We can do it after lecture. So Chapter 3 now, we're completely focused on derivatives. Chapter 3 is the biggest chapter in the book, and then Chapter 4 is just application of derivatives. So these two chapters, all about derivatives, constitute more than 1/3 of this class. So it's a massive concept, and this is what we're going to focus on for the next few weeks now. Just the concept of a derivative and its applications and how to calculate it. So let's remind ourselves what a derivative is, because we actually did this clear back at the beginning of Chapter 2. But let's rehash it out. So first, let's think about calculating the slope of a line. If I've got a line, there it is. How do I calculate the slope of the line? We get 2 points, pick a point x0, and any other point, we'll call it x. Then the height here is f of x0, and the height here is f of x. With me so far?
Mm-hmm. Yep.
So what's the slope of that line?
F of x naught minus f of x over x naught minus x.
F of x minus f of x0 all over x minus x0. Or you could flip the order of both those if you wanted. It's the same. So the slope is equal to that. Now we have a bunch of notation for the same things here. And so I think these first couple sections will be pretty easy in terms of the concepts, because we've already covered the big concept, how to calculate a derivative. The hard part is that we're going to have a lot of different notations represent the same thing. So the thing that I'm most worried about is you getting lost in notation and thinking that when you're solving a particular problem, you have to use a particular notation. So I'm going to rewrite this a bunch of different ways, and you'll see what I mean by it's just notation. It's not saying anything different. So if we call delta x the distance between these 2 points, then delta x is equal to x minus x0, right?
Mm-hmm.
You with me?
Yeah.
And we can also call the distance between these 2 points delta y.
Okay.
So I could also represent this as delta y over delta x. Different way of saying the exact same thing. Right? Mm-hmm.
Okay.
Now, if delta x is equal to the distance between those, notice that I can also say that x is equal to, move this to the other side, and I can also say, I have that right. I can also say x is equal to x0 plus delta x, right?
Yeah. Yeah.
So I can also write this as, another way we'll commonly show, is f of x0 plus delta x minus f of x0 all over delta x. You follow that?
Yeah.
Mm-hmm. One more thing. For some reason, the author often uses an h instead of delta x. So the last way that we'll see this is f of x0 plus h minus f of x0 all over h. Okay. Hopefully it's extremely clear how those are all saying the exact same thing.
And you're saying if we were to solve a problem, then we could use any of those. It doesn't matter.
Yeah, it doesn't matter which notation you use.
Okay.
Notice, here's often the case, is you're going to use one that looks like this. These two are kind of the same. These are probably the two I use the most, this one or this one. Why do I switch between them? Sometimes the algebra can be a little bit messy doing it this way since you're plugging in a sum for the term instead of just one term.
Okay.
So if for example, if my function were like f of x is equal to x to the n. Now, if I plug x into that, I just get x to the n. Notice if I plug x0 plus delta x into that, I get x0 plus delta x to the n. And that could be kind of messy algebra, especially if this was like a to the 6th. You don't want to have to expand that out.
Yeah.
So it's little situations like that where technically you're fine no matter what you use. It's just the algebra can be a little bit simpler if you are a little bit clever with which one you choose. Okay, so that's calculating the slope of a line. Now, what was a derivative? So now we've got some generic curve doing whatever it's doing. right? And let's say that I want to know the slope of the curve at this point, x naught. So I want to know the slope here. Here's f of x naught. We said, well, one thing we could do is pick some point to the right of it, call it x. So right here is f of x. We could calculate the slope of the line through these 2 points. That's going to be way off. See if I can do this a little better. Hopefully you understand what I'm saying, right?
Yeah.
Yeah.
I can calculate the slope of the line between those 2 points, and then that will give me an approximation for this point. Now that's a terrible approximation unless x gets really close to x naught. So as the x I choose gets closer and closer to x naught, if I were to pick this x instead, then we'd be even closer and our approximation would be even better. And if I got even closer, our approximation would be even better. So what is the slope at that point?
The limit?
It's the limit as x approaches x naught of the slope of the line. So here's the slope of the line.
Mm-hmm.
The slope at that point is now the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. You see how that's the same thing?
Good morning, I'm sorry.
Good morning.
We had passed, but good morning. I'm just looking for an extra power cord. You don't have anything in here, do you?
We have a ton right there. Take all you would like.
I'm just looking for, that might work. Look, do you mind? I'll return them.
I have no use for them.
If you don't
Hopefully
have
those
use
work.
for- Huh?
Hopefully they work. Feel free to come back and get these ones if they don't. These
Okay.
cords.
Okay, let me go see what they need. Somebody took all our stuff. I don't know.
Okay.
Good luck today.
Thank you.
I mean, I know you don't need luck.
Anyways, so now notice, as my x gets closer and closer to x naught, this slope gets closer and closer to the slope exactly at this point. And so the slope exactly at that point is this limit, when we calculate this limit. You with me?
Yeah.
So that's what the derivative is. So we say the derivative, well, we'll get into notation here in a second. But notice that this now, looking at all these, is also the same thing as the limit as delta x goes to 0 of delta y over delta x. Notice that x approaching x naught is the same thing as the distance between them, delta x getting smaller and smaller and smaller, right?
Yeah.
So this limit's the same as this limit. You with me?
Mm-hmm.
Which is the same as this limit. The limit, once again, is delta x approaches 0 of f of x naught plus delta x minus f of x naught all over delta x. And then finally we can replace the delta x's with h's, and we get the same thing.
Okay.
You with me?
Yeah.
Okay. So that is the derivative. Now, the notation that we use to signify the derivative, there's a bunch of different notations that we have, unfortunately. The first one that we use to talk about the slope of a function at a point, we say is f prime of x naught. So that's our shorthand. What's f prime of x naught? It's this. It's the slope of the function f at a point.
Okay. What's the reasoning behind that?
I understand the question.
F prime.
Why f prime? It's just notation.
Okay.
You just gotta call it something. It's associated with the function f. It's a different function. It gives you the slope of your initial, it gives you the slope of f. So let's get some intuition for this really quick. Let's graph the derivative of this function real quick and see what that would look like.
Okay.
So here's f of x, it's this line. So now what does f prime of x look like? What does the derivative of this thing look like? The slope function. So let's try and graph that real quick to give you some intuition for what we're talking about. What's the slope of the function right here?
I have no idea.
All right, just guess me. What does the slope of this line look like it is, roughly?
1/2.
1/2? Okay, we'll just call it 1/2. Doesn't matter. Picture's line.
Okay.
Okay, so what's the slope of the line right at this point?
1/2.
Right here. Oh, it's 1/2. So when we go over this far, we plot a point at 1/2. What about right here? What's the slope of the function?
Same thing.
1/2. And it's 1/2 here, and here, and here, and here. So the whole function is just 1/2. That's the derivative function.
Sorry, Mississippi, I'm just looking for a PowerPoint.
I just had some taken. There's extension cords here.
That's exactly.
Okay. Anyways, so notice how this is plotting the slope of this. This is a derivative function. If this is f of x, this right here is f prime of x. So it gives you a completely new function.
Okay, I'm a little lost how you went from the first initial function to the derivative function.
This right here is f of x. It's our initial function. F prime of x gives us the slope of this function.
Then wouldn't the slope always be the horizontal line for the derivative?
The slope is 1/2. This is going through the point 1/2.
Yeah, I'm saying for any derivative, wouldn't that be the case?
No. Now let's look at this monstrosity.
Okay.
So this is going to be a terrible picture, but we'll try to piece it together the best we can, just to establish intuition. So let's draw a real ugly graph now. And what we're going to need. Okay, so over here, notice that the slope is really negative, right? Like -8. So maybe core down here for our slope. And then it's getting a little less negative, a little less negative, a little less negative. So it's coming up. And about right here, the slope looks like it's 0, right? So this function is going to be 0 somewhere around here. So it looks like it's curving up here, something like that, right?
Okay.
Here the slope 0. Then the slope gets a little bit positive, 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 positive. It like starts out a little positive and then jumps up. And then it starts going back down, getting closer to 0. I don't know. We'll do some much nicer plots. But the point is, they're two completely separate functions. F of x is your initial function, f prime of x is the slope of that function.
Did you think them as kind of like reciprocals of each other?
No, the reciprocal of a derivative, if you want to think that way, is called an integral. And we'll get to that.
Can you show us what a parabola would look like?
Yes, we will do that exact case as an example, because that's the easiest one to do. Second easiest. This is the easiest, but it doesn't give us much intuition, just straight line. Anyways, so that's just me throwing it all at you in one go. Big picture of what we're going to be talking about.
Okay.
Okay, so now let's go through what the book actually has. So first thing they want us to do is to find the slope of the curve y equals 1 over x. So that's going to be our first example. So we're going to look at y equals 1 over x, and we want to figure out the derivative of it. We want to find the slope of this function at any point. Now let's get a sense for what this function looks like really quick. We've seen this one 100 times. We know it has a vertical asymptote here. We know it has a horizontal asymptote here. And it comes roughly like this. Geez, that was terrible. But you get the picture, right?
Yep. Yeah.
So that's roughly what it looks like. Something to notice about this, notice that the slope is always negative. The slopes are always going this way.
Yeah.
That's negative slopes. No slopes are going this way.
Okay.
So just quick sanity check, our answer better come out negative when we calculate this thing. Make sense?
Mm-hmm.
Okay.
Okay, so let's calculate the derivative of this thing. Now we can use whichever formula we like. I don't know. Should we use this one or should we use this one?
Let's do the first one.
You like this one?
Yeah.
Okay, so by the way, more notation. Sorry, you're just going to have to learn to bite the bullet. Another way that we write the derivative. Then y prime is equal to, and now we're going to calculate the derivative. Y prime is the same as f prime of x. Same thing.
Okay.
So maybe throw that up here while we're at it. Lots of notation saying the exact same thing. And like I said, that's what I'm most worried that is going to confuse you. Because you've already done this.
Yeah.
Okay, so let's calculate. This is the limit as, we were doing this one, as x approaches x naught. Oh, if we're going to do that, then let's write this as f of x. That keeps it easier. So I'll say f of x is equal to this. So then f prime of x is equal to, just to remind us, since I'm using s here, is the reason I'm switching it. Just
And
so that
since they're equal, it makes
seem
sense.
weird. Okay, so this is equal to f of x minus f of x naught all over x minus x naught. Right? Okay. Now what is f of x?
1 over x.
Yeah, now we just got to plug in. So this is the limit as x approaches x naught of 1 over x minus what?
What is f of x naught? Is it the same function?
Yeah, f's the same function. F is f.
That's right.
So 1 over x naught.
1 over x naught. All over what?
X.
X minus x naught.
Yeah.
Wonderful. Okay, this is equal to, little bit of algebra. I need to get the common denominator in the numerator. So I'm going to multiply this one top and bottom by x naught. I'm going to multiply this one top and bottom by x.
Okay.
Okay, so this is equal to x naught over x times x naught minus x over x times x naught all over x minus x naught. Kind of walking through it a bit slow.
Okay. Wait.
Oops, I forgot to write my limit sign. Still taking a limit. I just multiplied this top and bottom by x naught, so multiply it by 1, doesn't change it.
Yeah.
Multiply that by 1, doesn't change it. Okay, so now I have a common denominator, so I can rewrite that as x naught minus x all over x times x naught, right? And then the denominator, remember, if you divide by a number, that's the same as multiplying by the reciprocal.
Okay.
Follow the algebra there?
Yeah.
Now, keep track of what we're always trying to do with these limits. You've done a bunch of these limit problems, and remember that your problem is always, I can't divide by 0, I can't divide by 0, so you can't take the limit. And the whole goal is to cancel that stupid thing out of the denominator so that you can finally take your limit.
That's right.
So that's what we're out to do here. Now notice that I can almost cancel this out with this. They're almost the same, but not quite.
Yeah.
How can I make this look like this?
Negative.
Factor out a negative. Perfect. So this is equal to, sorry, I keep forgetting to write my limit signs. The limit as x approaches x naught of negative, pull a negative out of this term, and now we have x minus x naught over x times x naught times 1 over x minus x naught, right?
Yeah.
Okay. Oops, this is f prime of x naught. F prime of x naught because we're finding the slope of x naught.
Yeah.
Okay. Anyways, so this is equal to,
1.
cancel that out top and bottom. So I'm just going to put the negative with the 1 there. So it's just negative 1 all over, oops, still forgot my limit. The limit as x approaches x naught of negative 1 over x times x naught. Now we can take that limit, and what do we get?
You can take that
How
limit.
can you take the limit?
As x approaches x naught, what does x approach?
The same number.
Weren't you trying to get it to 0?
No, we made so it doesn't go to 0 anymore. Notice over here, look at over here.
Yeah.
As x approaches x naught, what's x minus x naught get closer and closer to?
0.
0. Can we divide by 0? No, that was our whole problem. Now we got that out.
Okay.
So now we're not dividing by 0 anymore. The limit of x as x approaches x naught is,
2x naught. Or,
well, no, this would be x naught squared, but I think you're getting it
yeah,
now.
that one.
So negative 1 over x naught squared.
Okay.
So that's the slope at any point x naught. So what is the slope of this function? What's f prime of 3 equal to?
Just
Negative 1 over 9.
Negative 1/9.
Yeah.
So if we were to go over 3 here, 1, 2, 3, then it has a really shallow negative slope,
Okay.
right? 1/9. What about -3?
You need positive, right?
No, still just -1/9.
Yeah.
You're right.
So this isn't as symmetric as it should be. Let me try just a little bit harder. And it's still terrible. But if we go over -3, we just get the same slope here that we got here.
Okay.
And now we can graph f prime of x. So we know that f prime of x now is equal to -1 over x squared. Right?
Yeah,
X squared.
because you just switch them.
Because I'm saying f prime of x.
Oh.
So, if we graph that function, what does that look like roughly? Let's see, it's going to have a derivative, one there, one there. And I think it's going to be like this. Something like that.
Okay.
How do you do that?
How did I graph that?
Yeah.
I'm already familiar with what 1 over x squared looks like. You could plot a few points and get the picture pretty quick.
Okay.
You could have plugged in something like -3, 1, 1/2, and got the picture from that.
So anytime you have the function of 1 over x, the derivative is always -1 over x squared.
Correct. Yeah, eventually we'll develop rules for calculating derivatives, so you don't have to go through all this work. So when I teach you the rules, you're gonna love it, but first we're gonna make you do it by hand. It's gonna be miserable.
Okay.
Fine.
Okay, so let's continue. So did that. What's this example? We knew that. Okay, so now they want to find the derivative of the problem that we did back in section 2. So let me erase this stuff. Let's do that. Remember the problem with a rock breaking off the edge of a cliff and falling? And we had a function for how it fell, and we calculated how far it fell in the first second, and then in the second, and then we calculated its instantaneous rate that it was falling right at the beginning of chapter 2. So going back to that problem. This time I'll use this derivative method.
Okay.
So going back to that problem, we have f of x is equal to 6, they use t, so let's use t, because time is what you plug in. So f of t is equal to 16 t squared. This is how an object falls. So if I were to let this go, after 1 second it would have fallen 16 feet. After 2 seconds, 2 squared is 4, 4 times 16 is 64, it would have fallen 64 feet. Now, our job was to calculate how fast it was moving, right?
Yeah.
How fast it was moving was its change in height over its change in time. That gives you speed.
Okay.
Displacement over time.
Okay.
Right? If I go 200 miles in 2 hours, what's my average speed?
100 miles.
100 miles an hour.
Yeah.
Right? Same concept. Well, notice that that's the same as just calculating the slope of this function.
Okay.
So the slope of a position function gives you, I'm going to say speed, but we'll come back and correct that a little bit. So the slope of a position function, this tells you where it is. The slope of a where function tells you how fast.
Okay.
Make sense?
Yeah.
So our job was to calculate, I think they specifically said let's calculate the instantaneous speed at time equal to 1. How fast is this thing moving? With me?
Okay.
Now, I'm just going to calculate it in general, and then we'll plug in 1 when we're done. Okay, so I'm going to say, what is f prime at any time t naught? And then we'll plug in 1 for t naught when we're done to get our final answer.
Okay.
Make sense? Okay, so what is this equal to? Well, this is equal to the limit as, now notice that we're in terms of t, so now it's going to be as delta t goes to 0, right? No confusion there. Since we changed this variable, we changed that variable.
Yeah.
Like I said, lots of notation, essentially saying the exact same thing. Okay, tell me what I'm writing.
F of t naught plus delta t, subtract f of t naught over delta t.
Perfect. Which is equal to the limit as delta t goes to 0 of what?
16, then you do the parentheses of t naught plus delta t all squared minus 16 t naught squared over delta t.
Perfect. Now, always keep in mind, what's the thing stopping us from just taking that limit?
0.
The denominator is going to 0.
Yep.
We got to get that delta t out of the denominator. That's our whole goal now. Okay, so let's distribute. Well, let's square that out first. I don't want to do too much algebra too fast. So this is equal to, keep the 16 here, times, it's going to be t naught squared plus 2 times t naught times t plus t, oops,
What?
sorry, delta t. Times delta t plus delta t squared minus 16 times t naught squared all over delta t. Once again, I forgot my limit. Oops. Just squared this.
2 times.
Then you distribute the 16, right?
T naught times t naught gives me this.
Okay.
T naught times delta t gives me one of those. Delta t times t naught gives me the other one. Delta t times delta t gives me the last term.
Okay, why is there no multiplication? Delta t there. Oh, never mind, I see it. I see it.
Okay. Any other questions? Okay, so let's run the 16 through and then we'll distribute. So this is equal to the limit as delta t goes to 0 of 16 times t naught squared plus 32 times t naught times delta t minus, or plus delta t squared, or 16 delta t squared. Thank you. 16 delta t squared minus 16 t naught squared all over delta t. Right?
Yeah.
Now notice the 16 t naught squared and the minus 16 t naught squared are going to go out.
Sweet.
And then one of these delta t's, and then we can factor delta t out of these two terms.
Yeah.
Okay, so this is going to equal the limit as delta t goes to 0 of 32 parentheses, because I'm factoring out delta t. 32, sorry, trying to make sure you can see what I'm writing. 32 t naught plus 16 delta t times delta t all over delta t. Good?
Okay.
Just factor it out. Cancel delta t top and bottom. And so this is going to equal the limit as delta t approaches 0 of 32 t naught plus 16 delta t. Now we can take our limit, and what do we get?
32 t naught.
32 t naught.
Yeah, I see what
So, f prime of x is equal to what? Or
32
f prime of t, we'll put t in there, is
Don't
equal to
you
what?
wanna do t naught in there?
32t.
Oh, okay.
T naught, we think about T naught as a particular point. This is now for any point in general.
Mm-hmm.
Okay, so here's our derivative of that function.
That's always the slope.
This gives you the slope. So if we were to plot this thing, 16t squared, which is a super, super steep parabola. Not sure I can even come close to doing it.
Parabola.
Yeah.
Just
Where's the square?
I'm saying the initial function.
Oh.
This is f of t. So that's f of t. The derivative then is a really steep line. And notice the slope over here is really, really negative, and it's increasing, 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 0 right here, and then it gets really, really positive.
Okay.
See that?
So it doesn't matter what number you put in. For the time you do 1,000, then the slope is always 32.
No, no, no. What's the slope at 0? Plug in 0 for t.
0.
0. What does that mean? That means the instant I drop the object, its speed is 0.
If no time has passed.
Yeah, t0, no time. What about t equal to 1? 1 second later. 1 second later, how far has the object fallen?
16.
16. How fast is it moving?
32.
32 feet per second.
Okay.
After 2 seconds, how far has the object fallen?
64.
64. What's its speed?
32.
At 2 seconds.
64.
64.
Okay.
So at 2, this thing and this thing better intersect.
Which it does. Okay.
So then, if it's, wait. That's the derivative.
Yes. This is the derivative of this.
So isn't that giving you the slope that you'll find? No.
This is giving me the slope of this at any point.
At any point.
Pick a number, 2. What's the slope of this function at 2? 64. So if you come over here at 2 and measure the slope of that thing, it's going to be absurdly steep, 64. For every 1 unit you go right, you go up 64.
And at 1, it'll be the slope of 32.
At 1, it should have a slope of 32.
Even though it's only at 0.16.
And at 0, it should have a slope of
0.
which a parabola does.
Okay.
And then notice the parabola has a negative slope on the other side.
Yeah.
So if you plug in -1, what's the slope now?
Negative 32.
Negative 32. So it has a slope of positive 32 at 1 and negative 32 at -1, which is good because it's a symmetric function. It's even.
Mm-hmm.
So we expect that. Okay, think you got that?
Yeah.
Okay, a bunch of notation for how we write a derivative now. Sorry. It's just how it is. So, we can write this as f prime, we can write it as y prime. Maybe I'll put them all over here. So you might see it as f prime of x, you might see it as y prime, you might see it as the derivative of y with respect to x. You might see it as the derivative with respect to x of f, or you might see it as the derivative of f with respect to x. Okay. Bunch of different notation, all saying the same thing.
All
All these are different ways of saying any of these. Always the same thing.
So why do we use so much notation?
Part of it has to do with the fact that both Leibniz and Newton were discovering calculus simultaneously.
Okay.
So Leibniz uses the notation with the d's in it. Newton uses the prime notation.
Okay.
So that's why we have both those notations. This notation is very, very useful, and we'll see cases where this is a very useful way to think about it, whereas this is often just a more convenient way to write.
Okay.
Yeah. So, one last thing I want to point out. One way that we'll often say, what's the derivative? Is, how's the right way to say this? There's going to be, is that jumping too far ahead? I'll just tell you. There's going to be math equations that come up in fields of math, including calculus, but tons of other fields of math in general, where you have things like delta y's and delta x's. And as a general rule, if you just take the limit of this thing as delta x approaches 0, then that gives you dy dx. So that's where the dy dx notation comes from. Replacing the deltas with d's of this.
Okay.
So this is talking about using some delta y, this is some delta x. This is saying an infinitesimally small delta y, or delta x, and delta y. So that's where that notation comes from. Thinking about it more like this, which I think makes pretty good sense.
Okay.
Okay, so let's keep going. So lots of notation, but you guys have been able to calculate these derivatives so far just fine.
Yeah.
So that's what I thought. The math you've already done before. You've already got the concept kind of. It's just a lot of different notations saying the exact same thing. So let's look at another example. The author wants to do f of x is equal to x over x minus 1. So we're going to calculate the derivative of this. Which formula should we use? Let's do it the author's way. We'll use the h's. Just because we haven't done it that way yet, and when you look in your book, you'll see him do it this way a lot. So let's see. So the derivative of this function at some point x naught is equal to the limit as h approaches 0 of f of x naught plus h. He just uses x. Minus f of x all over h. With me so far?
Yeah.
Yeah.
So far, just picking the notation that we're going to use. Now we'll actually plug in. Okay, so this is equal to the limit of, what do we get when we plug x plus h into this thing? We're going to get x plus h in the numerator all over x plus h minus 1 in the denominator. So that was, sorry, that's plugging in this term. This is right there. Minus f of x all over h.
Okay.
Just plugging in.
Yeah.
Good. Okay, now I need to get the common denominator in the numerator. So this is equal to the limit of, I'm going to multiply this one top and bottom by x minus 1, this one top and bottom by x plus h minus 1. So we're going to get x plus h, oops, what did I write a b? X plus h times x minus 1 minus, that's that minus, x times x plus h minus 1 all over. Now we have a common denominator, x plus h minus 1 times x minus 1, all times 1 over h.
Okay.
Just plugging in so far.
Now do
Well,
you factor
factor
out
out.
a negative 1?
Well, no, I'm going to distribute all this out. And hopefully when I distribute all it out, there's somehow an h I can cancel out.
Okay.
Because remember, it's still this h that's stopping me from continuing. Because this is the limit as h approaches 0.
Yeah.
So this is equal to the limit as h approaches 0 of, and let's multiply that whole thing out. So let's see, we're going to get x squared plus x times h minus x minus h minus, I'll distribute this minus when I'm done, so I'll put brackets here and just distribute the x around the other one. Minus x times x is x squared plus x times h minus x. All over the denominator we don't need to worry about. Times 1 over h. You follow that?
Yeah.
Okay. So notice we have an x squared and a negative x squared, so those go out. We have a positive x times h and a negative x times h, so those go out. We have a negative x and a negative x, so those go out. So in the numerator, what are we left with?
Negative h.
Negative h. Perfect. So this is equal to negative h all over x plus h minus 1 times x minus 1 all times 1 over h. Now the h's go out, leaving me what in the numerator?
Negative 1.
Negative 1. So then this is equal to, oops, forgot my limit. The limit as h approaches 0 of negative 1 all over x plus h minus 1 times x minus 1, which is equal to negative 1 over what? Tell me what to write.
X
Minus 1 squared.
subtract 1.
Perfect.
There you
X minus 1 squared. There's our derivative.
Okay.
That's it. That's all we're trying to find.
go. Okay.
I know, too easy, right?
Well, we're going to be doing a ton of these for our homework, right?
Oh yeah, you'll calculate so many derivatives that you'll look at stuff like this and you'll be able to calculate it super fast. You think I'm kidding? You will be able to. It's just going to be a little bit. Okay. Next they want us to calculate the derivative of a square root function. Okay, so here we have f of x is equal to the square root of x. Which notation should we use?
Let's do the middle one.
This one?
Yeah.
Okay. So, f prime of x is going to be equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, right? Now we just plug in. This is equal to, tell me what to write.
Square root of x plus delta x
Perfect. Minus
minus square root x
all over.
delta x.
Perfect. what do we always do when we have square roots and we're not sure how to continue?
Multiply by what makes it easy. But,
Multiply by what makes it easy.
yeah.
Switch the sign from a negative to a positive, and if that were positive, we switch to a negative, and multiply that top and bottom to the fraction.
That's right.
So, this is going to be equal to the limit as delta x goes to 0 of, we have, well, I'll just write right here. So, we're going to take this and we're going to multiply top and bottom by square root of x plus delta x, oops, plus the square root of x, all over square root of x plus delta x plus square root of x. Remember, we can always add 0 or multiply by 1. In this case, we multiplied by 1.
Okay.
Good? All right. Now, let's distribute. So this is the limit as delta x goes to 0 of, now since we chose it this way, our square roots go all the way, so we're going to have x plus delta x, that's going to be this times this. We don't have to worry about the middle terms, and then minus x for this times this. So that's our numerator, right?
Why is it?
Which is just delta x, right?
Yeah, but I want to,
Doesn't that get rid of,
Okay.
because you have a negative root of x and positive x, and then just get rid of it? No.
negative square root of x times positive square root of x gives me negative x.
Yeah.
That makes sense? Okay. And then in our denominator, we still have delta x times the square root of x plus delta x plus the square root of x. Right? Now notice, x goes out with x,
And then the delta.
and then delta x is canceled. And so this is just equal to the limit as delta x approaches 0 of 1 over square root of x plus delta x. Am I writing way too small?
No, I see it, just like.
Try and write it a little bigger. Square root of x plus delta x plus the square root of x, right? Okay, what is the limit of that as delta x approaches 0?
What?
Take the limit.
The root of x plus the root of x.
Well, under 1.
Okay, so it's equal to 1 over 2 square roots of x.
Okay.
Wait, aren't the square root of x being added together, not multiplied together?
Multiplication, distributed addition.
Yeah, they are being added together. So if I have 1 here and 1 here, how many do I have?
Oh, that's right.
Multiplying square roots would give me an x.
X, yep.
Okay, so there we go. That's our derivative function.
Okay. I'm confident that I can do that now.
Think you could calculate a bunch of these?
Sure hope so.
I sure hope you can too. The author in section 3.2, he has a lot of pictures trying to help you get intuition for the fact that the slope, that a derivative gives you the slope of a function. So looking through 3.2, if that's still a little bit hazy, might be useful. Okay, let's see. Show that the function absolute value of x is differentiable everywhere but 0.
What does he mean by differentiate?
Oh, sorry. If you can calculate the derivative at a point, then we say it's differentiable at that point.
Differentiable.
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 Uh-huh.
Gotcha.
If you can calculate the derivative of a function, then the whole function is differentiable. If you can calculate the derivative at a point, then it's differentiable at that point.
It's kind of like how the whole
whole function does not have a limit.
Yeah, it can. The whole function, the limit.
Oh, you can calculate the limit anywhere on a function.
Okay.
That is possible. Is that what you mean?
Yeah.
Sorry. I just meant you can't just take the limit of x squared.
Yeah, you have to.
Yeah, you
put-
just have to say the limit as we approach the point. Okay. So now let's look at f of x equal to the absolute value of x. Oh, before we do that, let's just do it for lines in general. Because that will be useful.
So the parabola one you said you were gonna do is just that one up there.
Yeah, we could do another one if you wanted, but
So it always just has the line going through, hitting 0, unless there's y-intercept and going negative.
sorry, what?
Is that what it looks like in general for most parabolas?
Yes, for every parabola, its derivative is going to be a straight line.
Yeah, that makes sense.
And the less steep the parabola, the less steep the derivative line. Anyways, so let's look at absolute value of x. Now remember what absolute value of x gives us. If x is positive, it gives us x. If x is negative, it gives us negative x. Make sense?
Yeah.
You plug a negative 3, you get negative 3 out. Okay. And we know what this function looks like really quick, right?
Yeah.
Absolute value of x, it looks like this, and then like this.
Okay.
Now notice just intuitively, since this is a sharp point right here, if I drew that good, what's the slope at a sharp point? So it's a sharp V like that at the bottom. What's the slope at that point?
At the point 0, wouldn't it just be 0?
Remember how we get the slope, we say the tangent line that goes through it, but there's a bunch of tangent lines that go through it. Here's a tangent line that only goes through that point. Here's a tangent line that only goes through that point. Here's a tangent line that only goes through that point. So intuitively, sharp points shouldn't have a derivative. You can't get the derivative at a sharp point.
Okay.
You can't talk about the slope at a sharp point.
Okay.
So intuitively, that's what we should expect, and we'll see that coming out in the math. Oh, before I did this, I said we were going to do just a line. So let's look at f of x is equal to mx plus b. Just any line. What's the slope of that line?
M.
M. So what should the derivative be?
And,
M. Let's calculate it and make sure that that's how it actually comes out.
okay.
With me?
Okay.
Okay. Let's go back to the first one, because why not? So we're going to look at the limit as x approaches x naught of mx plus b minus mx naught plus b all over x minus x naught. You with me? F of x minus f of x naught all over x minus x naught. Okay, so what are we going to get?
When you simplify?
Yeah, so first notice that b's are going to go out, right?
Mhm.
We have positive b and negative b here.
And m's are gonna go out.
No, you can't do that. You can factor them out. You can't just get rid of
sorry,
them.
yeah.
So it looks like that, right?
Mm-hmm.
Yeah.
Okay, factor an m out of the numerator. Oops, my limit. Factor an m out, we get m times x minus x naught all over x minus x naught.
Okay.
Cancel them
Let's
out.
cancel out. It's equal to the limit of m. The limit of a constant is always just that constant.
Okay.
So that's just proving.
Mm-hmm.
Sick.
So now you know, for any straight line, how to calculate its derivative.
Okay.
It's just a slope. Surprise, surprise. Okay, so So now let's do the absolute value function.
Wouldn't that just be undefined?
What?
Because on the absolute value, there's that sharp point, wouldn't it be undefined at that point?
Oh,
Derivative?
we'll get to that. Remember that a derivative is a limit, right?
Yeah.
And when does a limit exist? A limit exists when the function is defined at that point, and the left-hand limit and the right-hand limit give us the same thing.
Okay.
So what we're going to do is calculate the left-hand limit, calculate the right-hand limit, and show that they give us different things.
Okay.
And so the limit at 0 doesn't exist.
Okay.
But first we'll talk about the limit, or we'll talk about the slope. Well, we probably don't even need to write anything down for this one. So what's the slope of the function everywhere not 0 on the left-hand side?
Negative x.
Just -1,
-1, sorry.
right? Because this is just the line -x.
Mm-hmm.
And what's the slope here?
Just one.
So we know it has a derivative. We know it has a derivative 0 to infinity, and we know it has a derivative. We know it has a derivative from -infinity to 0. So here's where it's differentiable. We're going to show it's not differentiable at 0. It doesn't have a derivative at 0. Anywhere else we can calculate the derivative. Make sense?
Mm-hmm.
Okay, so let's do it. So now we're going to look at the limit as x approaches 0 from the right of absolute value of x minus absolute value of 0 all over. Maybe I should have had you guys tell me what to write here.
That works.
You see how this was just using this?
Yep.
It's just now our particular point was 0. So hopefully you don't get lost when suddenly we got our actual number in there again.
Yeah.
Okay. So approaching 0 from the right. So we know absolute value is always positive. So this is equal to what?
X minus 0 over
X
x minus 0.
minus 0 over x minus 0. Oops, limit. Which is equal to what?
1.
The limit of 1, which is equal to 1.
Mm-hmm.
Good? Which is
Yeah.
what we expected. The derivative over here, always 1.
Okay.
So that's also the case as we approach 0. Now, if we would, well, we'll keep that there. We'll just write down here. Now, if we look at the limit as x approaches 0 from the left of this, what do we get?
Negative x.
Negative
Plus 0.
x over x.
Yeah.
Limit. Those cancel out, leaving me with
Negative 1.
-1,
Which is not the same as the first.
which is not the same as this. So the limit as x approaches 0 of f of x does not exist. Because its left-hand limit and right-hand limit were two different values.
Mm-hmm.
The limit exists if and only if both these exist and give us the same number. Make sense?
So what would the function for the
Derivative function would look like this. Do 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 do. Do 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 do. Oh, I did that backwards.
You did, but I get the picture.
It should be, yeah, -1 over here, +1 over there. Sorry. All right, so that's absolute value x. Okay. Last thing we have to cover is that differentiability implies continuity. What does that mean? That means if a function is differentiable at a point, then it's continuous at that point. If I can calculate the derivative of a function at a point, then the function has to be continuous at that point.
So what's the difference between derivative and continuity?
Continuity and derivative?
I mean,
Derivative is giving me the slope. Continuous is,
just if it is.
here's continuous, oh, not continuous there, and then continuous here. Right?
Mhm.
Our theorem is going to say, well, if you know that you can calculate the slope at a point, then you also know that the function is continuous at that point.
And you get free time?
So just because it's continuous doesn't mean it's differentiable.
You can,
But if it's differentiable, then it is continuous. Here's an example of one that's continuous but not differentiable. This function is continuous at 0. It is not differentiable at 0.
can't you find the limit at that point, even though it's not continuous there? Can't you find the limit at whatever that circle is?
Yeah, I can find the limit as a function approaches that point, but that's not what continuous meant. What did continuous mean? Continuous was the limit as x approaches c of f of x is equal to f of c. This is a definition of continuity, sorry, that's an x. So let's
Yeah.
throw something up here. Let's call this point C. Let's say that this value right here is f of c, right?
Even though that's not what the limit is, yeah.
So notice in this case, the limit as x approaches c of f of x is not equal to f of c, so it's not continuous at that point.
So what do you mean when you say if you find the derivative at that point? I get it.
Then it's continuous.
I get it.
Okay. So differentiability implies continuity. The converse is not true. That's what we're going to prove. So I'm going to use the fact that I know, so I'm given that the limit as x approaches c of f of x minus f of c all over x minus c, I'm given that this exists. That's a number.
Okay.
And I'm trying to use that to show that this implies that the limit as x approaches c of f of x is equal to f of c.
Okay.
Okay?
Yeah.
Let's get some space. So let's think what we can do. So I know that the limit as x approaches c of f of x minus f of c for x minus c, I know that exists. So I know that that's equal to something. We'll just call it f prime of c, because that's what it is. So then I know that the limit as x approaches c of f of x minus f of c is equal to f prime of c times x minus c. Just multiplying both sides by x minus c.
Okay.
So now I know that the limit, but now we still need it, we also need to take the limit over here since x is approaching c. So this is equal to the limit as x approaches c of f prime of c times, remember f prime of c is just a number, it's constant. So f prime of c and the limit as x approaches c of f prime of c is the exact same thing.
Okay.
Because the limit of a constant is a constant. So there's no problem with me adding that there, right?
Okay,
And now I'm moving the x minus c over here. Good?
then you add the f of c to each side.
And then add f of c to both sides. That's exactly right. So this is the limit as x approaches c of f of x is equal to the limit as x approaches c of f prime of c, parentheses here, f prime of c times x minus c plus f of c. Follow the algebra?
Yeah, and x minus c is just 0, right?
Yeah, calculate the limit now. X minus c as x approaches c is what?
0.
0. So this becomes 0. 0 times any number is still just 0. So it's just equal to f of c.
Where did the f of c come from there?
It was initially here
Oh.
at both sides. So if it's differentiable, then it's continuous.
Okay.
Good? Alright, so that gets us through 3.1 and 3.2. Strongly recommend actually reading 3.2 yourself because derivatives, like I said, they're a huge part of the class.